It is 2 in the morning on a highway shoulder. An officer approaches a stopped vehicle. In this exact moment, safety dictates knowing exactly who is behind the wheel. Are they armed? Are they wanted? In the 1960s, a driver could commit a crime in Nevada, cross the border into Florida, and effectively disappear. The newly built interstate highway system allowed people to move freely, but the information about them hit a brick wall at the state line. Every state maintained its own isolated vaults of criminal history, active warrants, and vehicle registrations. None of these local systems were wired to talk to each other. If an out-of-state plate was pulled over, the officer had zero visibility into that driver's past. A routine traffic enforcement stop became a blind risk. Rather than attempting to build one massive central database, the U.S. engineered a decentralized message router called NLETS. It acted as a digital switchboard, translating and connecting 50 incompatible state networks. The engineers operating this switchboard faced a punishing constraint. To be useful, the network had to send a query to a foreign state's database, extract the specific record, and return the answer in 300 to 800 milliseconds. That sub-second latency requirement exists for one reason. An officer is standing fully exposed on the side of a live highway. The network has to operate at the speed of the traffic stop itself. The original 1970s NLETS switch operated on early minicomputers, moving data over 300 baud leased telephone lines. It relied on a custom assembler-level routing protocol. This network was deployed before the public internet, before TCP/IP, and long before fiber optics existed. The original system was built as a mesh of state control points, using an assembler-level router designed to survive individual node failures or local circuit cuts without taking down the national query grid. Using analog tape drives and early processors, they delivered sub-second latency across narrow 300 baud lines, hitting performance targets that modern web services still struggle to maintain. This schematic illustrates the hub and mesh hybrid topology. Each state operates a local switch, plugging directly into the central NLETS core. The mesh has overlapping redundant circuits. If a line is cut, the data automatically finds an alternate pathway. Because of this structural redundancy, no single state outage or localized hardware crash can isolate a region. The national enforcement grid remains continuously active. To guarantee data survives that journey, the system rejects flexible programming formats like JSON or XML. Instead, it uses a fixed-width, position-encoded text block. Every piece of metadata is locked into a specific slot. This deterministic format is easy to parse on low-power hardware and remains readable even if transmission errors corrupt a single bit. By choosing predictable structure over modern software standards, this payload can bridge 50 different state databases without breaking the chain. Today, the tape rails are gone. The network runs on a redundant AWS GovCloud deployment, featuring modern load balancing and TLS encrypted connections. Yet underneath the cloud architecture, the core logic of the message switch remains the same as it was in the 1970s. The routing rules have survived 5 decades of hardware upgrades. That logic now commands a massive footprint. A single query can pull data from Canadian law enforcement, the TSA, and international watch lists. Through all this expansion, the system remains strictly a message router, not a database. It stores no central records, ensuring that every state maintains control over its own data. Right now, an officer is standing on the shoulder of a dark highway, waiting for a license plate return. This invisible architecture will process that query, cross state lines, and deliver the answer, securing the scene at the speed of a traffic stop.